The Autonomous Operating System, the AOS, model-based plug-and-play autonomy for robots in partially observable probabilistic domains with noisy sensing, a research of Orwer, Time and Dan Suissa under the supervision of Professor Ronen Brafman. Motivation. An increasingly wide range of robot skills is currently available. How can an autonomous robot use them to perform tasks? The current state of the art is to use handwritten scripts or state machines to schedule skills into effective behaviors. The challenge is that scripts or state machines are non-optimal and hard to maintain upon environment change or robot skill upgrade. The solution is to use AI planning algorithms to control the robot. The problem is that it requires AI expert and a significant integration effort. Our goal is to provide plug-and-play task-level autonomy for robotics. Our solution, the Autonomous Operating System, the AOS, which offers several advantages. Conceptually, we provide full POMDP support with stochastic actions, partial information, noisy sensing, complex goals, and optimized behavior while balancing trade-offs. We offer an abstraction mapping, which is an explicit and principal mapping between the skill model and skill code. We use generative POMDP models that are based on probabilistic programming language. It offers greater expressive power, easier to specify, and enables much faster sampling rates, which are important for sampling-based algorithms. Engineeringly, we provide a true plug-and-play system. Given properly documented skill code, no additional programming effort is needed to integrate it with the system. Documented skills can be added incrementally and used by the system. The AOS uses reinforcement learning to auto-generate MDP heuristics for POMDP solvers. The system has a graphical user interface to visualize the robot belief state distribution and understand the robot behavior. So how do we use the AOS to develop an autonomous robot? We will go over a simple example. Our lab has a panda cobot, a robotic arm, and we wanted to play tic-tac-toe versus a human. To do so, we need two basic robot capabilities: drawing a circle in a desired square and detecting the board status after the opponent's turn. We refer to the robot basic capabilities as skills. The skill development is out of the AOS scope, so we implemented the needed skills. For the draw skill, we implemented a PID controller to draw a circle on each tic-tac-toe cell. For the detection skill, we attached an IntelliSense camera to the robot arm and used an image detection code downloaded from the web to translate the image to a string representing the board state. The skill inspects the board at a certain frequency and reports the board state after the human players altered it. The second step after implementing the skills is documentation. We start with the environment file called EF. It is used to specify the skill-independent aspects of the model. These include general POMDP parameters, state variables, terminal states, and state-dependent rewards. On the left, we see the general POMDP parameters for tic-tac-toe, the horizon, that is, how many steps to look ahead, and the discount factor, how much less future rewards are worth in comparison to present rewards. We also describe the state variables. These can be of any primitive C++ type or vectors of them. Users can also define custom enums or compound types. In this example, we define an enum called symbol, which is the type of the grid cell content. It is either empty, O, or X. There are two state variables, the grid cells vector and whose turn it is. On the right, we see the reward code, which describes the terminal states and specifies state-dependent rewards. Here specifically, rewards for winning, losing, or a tie. As you can see, the domain specification is compact and flexible. Notice the use of code in this specification and future ones. This is important conceptually because we are moving from declarative models to generative models. Code provides much greater expressive power. This makes it easier to write the model and makes the model more compact and hence easier to understand. We also exploit the code to make sampling, which is used by Monte Carlo algorithms, more efficient. Finally, users can define extrinsic changes not invoked by the robot. Here we define the human player's behavior of marking one of the empty cells with a uniform probability. This is not the best policy, but it's enough for our example. The next step is to document the skills. There are two files, the SD and the AM file. We can see the SD file for the detect skill on the left. Semantically, an SD file specifies a fragment of a POMDP model associated with a specific action or skill. It describes the expected high-level impact of applying the skill, how state variable values change, the associated reward or cost of the skill, and the information the skill will supply. In the POMDP model, these are called the transition, reward, and observation models. Detect has a very simple dynamic model, as it does not impact the world, so there is no need to specify a transition model. The reward model is very simple. There is a soft precondition that the detect skill should be applied only when it is not the robot's turn, with a penalty of -10 if violated. And the skill has no cost. The observation here is simply a string that describes the board status, which is assumed to be accurate. On the right, we see the abstraction mapping, or AM file, for detect. The AM file connects the more abstract model of the skill with the skill code. It specifies how to activate the skill code, possibly conditioned on a skill parameter, and how to translate the result of skill code execution, including return values and other code level parameters, such as ROS message values, to an observation corresponding to the model as specified by the SD. In this case, we use the detect skill to activate the observe tic-tac-toe board service, and the response called an observation is the value of the OBSR local variable. The OBSR local variable is taken from the robot code return value. In general, local variables are used to define events that occur during code execution and more, as described in our paper. We now describe the draw skill documentation. On the left is the SD. In POMDP terms, this SD file describes an action template. The skill receives a cell position parameter, and there is one concrete POMDP action for every possible position. The possible values of skill parameters are described in the available parameter section, an array of tuples that contains the possible context of a skill activation. Cell position can be 0 to 8 here. The precondition is not to activate the skill when it is the human's turn and to only mark empty cells. In the dynamic model, we define that given cell is now a circle or an O, given it was empty, and that the observation is always success. So this is a simple deterministic action. The AM file on the right plays a similar role as the detect AM file. As we can see in the video, it works well, but was the effort justified for such a simple deterministic game? Why shouldn't we write a script instead? Now let's think what happens when something changes. If the robot is now faulty and succeeds marking the center cell only half the time. If it fails, the turn passes to the human player, Changing a script is not trivial, even for this simple change. And another example, what if we want to use the same skills but for a different objective? We now play a new game whose goal is to mark cells adjacent to the corner cell with the player symbol. Adapting a script to a state machine to play this game is non-trivial. In the AOS, to handle the faulty arm, we only add a line to the SD file saying that the success is sampled from a Bernoulli distribution of 0.5. If the skill parameter is the center cell, and we add a new second possible observation of failure. The AM file should have a minor update handling the possible failure observation. That's it. The AOS now optimizes the robot action under this new model. You can see that it tries to win without using the center cell unless it's crucial. And again, for the new task, we just need to change the state-dependent rewards in the EF file. The AOS allows the definition of a one-time reward, making it easy to describe our new objective. Our next experiment involved a simulated armadillo robot, a mobile base with an arm. To test the POMDP model's advantages given partial observability, noisy sensing, and stochastic effects. The simulation environment included a room with 2 tables, each with a can on it, and a corridor with a person. One can is very difficult to pick. Its true height is 10% of the height perceived by the robot. The robot starts near the table with the difficult can. Its goal is to give the can to a person. We implemented 3 skills: pick can, navigate to a person or a table, and serve can to a person. We used 2 versions of the pick SD, a rough model that assumes that the probability of a successful pick is independent of the selected table, and a finer model in which the success probability is conditioned on the robot position. First, we experimented with each skill and used the observed statistics to write their SD files. Then we specified the AM files and the task. This information suffices for the AOS to control the robot throughout the task. We observed that pick returned success if motion planning and motion execution succeeded, which did not imply that the can was successfully picked. Therefore, we enhanced our pick AM file to listen to ROS topics published by the arm driver, like gripper pressure and arm joint angles, significantly improving the observation model accuracy and the resulting policy. The toy collection domain. In this problem, the robot should bring the different toys marked as colored balls to the child, which is marked as a box. There are 5 locations, 0 to 4. The child is at location 4. Each toy is located in one of 4 locations, 0 to 3. A complex distribution describes the toy's initial location and value, which ranges from 10 to 40. Placing a toy near the child has a utility of the toy's value. The robot has 3 skills. It can pick adjacent toys. Picking each toy is different. The pick only succeeds if the adjacent toy's color is given. This skill accurately reports success or failure. The robot can place a toy it is holding near it. This action succeeds and reports so if the robot is holding a toy. Finally, the robot can navigate to each of the 4 locations. The navigation success probability depends on the destination. The robot stays in the same location if navigation fails. The navigation module noisily reports if the navigation was successful or not. And to conclude about this domain, the toy collection problem is a partially observable domain with probabilistic action effects and noisy sensing. These are common characteristics in robotic domains. The needed skills were implemented and documented, and we used the AOS to solve the problem. In the left corner we can see the gazebo simulation, and in the right corner we see the AOS GUI that interacts with the AOS Web API. Let's talk about the GUI. The AOS exposes a RESTful web API. We implemented the GUI to assist in the fast development of autonomous robots. Users can generate new domains, debug them visually, and inspect robot execution in real time or after execution. The robot's belief at any time is visualized using graphs that show the distribution over values of each variable. These graphs are easily filtered. Additionally, users can add a Python script that translates a single state into an image. The GUI uses this script to build a combined image representing the robot's belief state distribution. In the GUI, you can see an image representing the robot's current belief. Rows 1 to 4 corresponds to toys 1 to 4. Each toy has a color. Row 5 describes the robot location. Columns 1 to 4 represents locations 1 to 4. 4 is the child's location. Column 5 displays toys in the robot's arm. Color intensity describes the object location probability. Graphs presents variables value distribution, which can be filtered. At each point, the previous action and the observation received are displayed in text, as well as the current action being executed. This example emphasizes the advantage of using POMDPs. See how actions are selected based on the belief state distribution rather than a single possible state. When the belief state is visualized, we can see the reason in the robot action selection. See how applying probabilistic actions like navigation adds uncertainty to the belief, and how observations focus the belief based on their accuracy. Failed or successful pick actions supply valuable information that reduces uncertainty and assists in future decision making.